Okay, so we're going to talk about some basic optics, like I said, and the idea here is that we're going to compare a little bit between the eyes and the brain and the camera again, and we're going to compare, we're also going to talk about some basic optical principles, all right? One of the things to remember about our eyes, we talked about accommodation in previous lessons, our eyes can compensate as well as accommodate. In other words, accommodation is strictly that flexing of the lens to make focus change. You know, when you hold your thumb out and look into the distance and look close up, that exercise. But compensation also means that the brain and the eye can work together to fill in details of an image that aren't completely clear. And cameras don't do that. Cameras are presented an image and they capture the entire image essentially as it sees it. So one of the things that the eye can do, it can look around to encompass a broader angle. And it can do some of this look around because we're, as we said before, we're scan viewers. And that means that we look around a scene and fill in the details as we need them. Right? So for example, this scene of Studio One, you'd be standing in this position, looking, say, for example, at the camera that's in the center of the, near the center of the frame. Well, what's weird about the human eye and brain is, even though you're standing right here where this image shows you, when you look at that camera, it sort of tends to fill your vision. It's not that it gets any bigger. This is very hard to describe, but your focal attention and your brain's attention span narrows down onto this object and you start looking at it in detail. So you start to discount everything else that's happening. So this is the same phenomena that allows someone to sneak up on you. You'll be in a situation where someone can sneak up without being right behind you. They can be kind of off to your side, but you don't see them because you're so focused on what it is you're looking at, right? So that's something the brain can do. So eyes can also instantly change focus at various distances. We did that exercise with the thumb the other week there, and you can instantaneously go from the gnome in the front to the gnome in the back to the gnome in the middle without really moving anything other than you having your lens change its shape because your brain says, look over here, look over there, right? Plus, the other thing that we have going on besides those two things is the brain builds an image. So what's really important to remember when we're talking about optics and vision is that optics and vision are an animal of physics and science. They're simply capturing the data, which in this case is light rays, and manipulating that data in geometric fashions to get it to a certain position, i.e. the focal point. But our brains use some of that geometric work in the eye with the fluids and the cornea and the lenses, but at the same time, the brain, using some of its conditioning, can create images based on small amounts of data. And the classic example is that whole idea of seeing somebody's face in a piece of toast. I say it because you should know about this, sort of, it's a meme slash, myth slash thing. But it tends to be, and this is what's weird about this, if you think about it for a second, it tends to be a couple of particular people. Is if you don't believe in certain religious beliefs and someone shows you that same piece of toast, you don't see that image. It's there. In other words, the data that created the image for the first person is there, but their brain has convinced them that it made a pattern out of it that they can relate to, right? So that never happens with a camera. Never, 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 never. A camera doesn't see an image and say, oh, I think that's, the camera doesn't think anything, right? It's just capturing the data. How do they capture this data? Well, they capture this data with lenses. We're talking about cameras now. So the eye does too, right? The eye has a single lens and a cornea. So it's a compound system. Like these various lenses here are compound systems. In other words, you can guarantee that inside of each one of these four lenses in this picture are multiple elements. Camera lenses are made from transparent materials like glass. That's pretty obvious. Or plastic acrylic polycarbonate. It's important to recognize, however, that these are man-made materials. Like our eye, which is, it's not that it's man-made, but our eye is a created material. It's not some magical theoretical material. So like the eye, optical lenses and stuff are created, in this case by humans, and those created items have flaws. That's the whole point of that ramble, is that they're not perfect. Nothing is perfectly created. It's all as close as possible, right? Basically, it's just a recipe. It's like making pancakes. You take a bunch of different things, you mix them together, you heat them up, and boom, you've got glass. The trick is, and this is why I talk about this little sidebar a little bit, is when you come to buy lenses, for most people starting out in filmmaking, it's the last thing they think about is the quality of the lens. Typically, you're much more utilitarian in that I'm buying this camera, I need a zoom lens, I need a wide angle lens, and I need a telephoto lens, or I need a portrait lens. That's how you're thinking, and that's fair enough because that's where you're getting into. But as you move up the continuum of photography and cinematography into the professional realm, what happens is you begin to be concerned about the quality of the image. And for example, when you get to 4K and shooting in 4K, flaws in the glass become an issue because they're much more visible than they were in the old days of standard definition, or in the case of videos coming out of phones, which are heavily compressed, right? So the impurities in the lenses aren't even noticed because the impurities in the compression of the image itself, the digital image, is much more noticeable. But when you're into 4K and higher shooting equipment, you're going to have high quality glass, right? So it's not something to worry about right off the bat in your career, but you should start learning about it, because it's like anything. If you start to play tennis or you learn to play hockey, you buy the sort of cheap, we learn to drive often. Your first car is kind of a car that, well, you know what, if I hit a couple of parking dividers, you know, if I sideswipe somebody, no big deal, I'm still learning. I'm not recommending you sideswipe people when you drive. But the same is true with shooting. You buy your first camera, your first kit. It's not going to be your last kit if this is going to be the way you're going to travel throughout your career. But you want to start learning about quality stuff right away, right? There's a video here, this Nikkor video, because they kind of show you the process of glassmaking. You can see it's quite involved. Okay, so let's talk about some of the mechanics again, just go over some of the principles we talked about before. The focal point, right, is that theoretical point where all light rays converge, and it's on the principal axis. So the principal axis is this horizontal line that runs through the physical center of the lens. So if we looked at these light rays here, these diagrammed light rays, this middle light ray would be going down the horizontal axis, which is the principal axis. And the principal focal point is the one that's on this line. Why do I say the principal focal point? We'll talk about that in a second. The focal length is the length from the vertical center that runs up and down through the lens, to the physical center of the lens, right? Or pardon me, the optical center of the lens, where the light ray bending is at its midpoint, is the vertical center. The focal length is the distance between that vertical center and the focal point. That is the focal length. So that is, the focal length is not this way to the left. That's the focal distance. And we'll watch a video in a second, and I think the guy makes that mistake in the video, the narrator. Okay, so what does that all mean? Well, that means, obviously there isn't a single image, a single point on a sensor that is the image. There's a whole area, right? Well, how does that work? Well, as the light rays are gathered by the lens, and you'll see this in this illustration here, and I'll repeat it again, it'll stop after a second. Let me just go back. And what this is kind of, let's go back again, start it again. What this is kind of showing us is that the light's coming from all different directions. It's not so much scanning along this line the way it's illustrated, but in order to make it clear, the light's coming from all directions. Well, all the light that passes through this lens focuses on one single line that crosses the principal focus and the horizontal axis, right? That line, the vertical line, is called the focal plane. That is a flat surface at a distance from the lens where the focal points exist. So it's the same distance away as the focal point in the center, all the way up and down a line. It's a straight line, which is how we are allowed to have sensors in the first place. If we didn't have that straight line, then you couldn't put a sensor there. But because we have this principle working for us in physics, it's possible to put a sensor or a retina at this place, right? So, one more time, just to get the points clear. Focal length. So this focal plane is actually focal points all the way along. And all the way along, not just up and down, but in a square, right? In an area. It's a square. It's not really a square at all, to be honest. It's actually a circle. So I'll just sidetrack for a second. The amount of light that comes into a camera is not defined. No, stop that again. Let's try that again. Take two. The shape of the image captured in a camera is defined strictly by the piece of sensor. However, the light that comes into that sensor is round. It's the same shape as the lens. So whatever shape the lens is the shape of the image that falls on the sensor. The sensor crops most of that light away, and all that's left is what's the sensor's own shape. Does that make any sense? So we have a 16:9 image sensor in a camera. Well, there's much more than a 16:9 square being seen, if I want to use the word, being reflected inside that camera, but we don't care about it. We only want that rectangle that we're going to use because our screens are rectangular, right? Whereas in the human eye, there is no such limitation. The lens is round, and therefore the image that falls on the retina is also round. The image that falls inside a camera is round, but there's a square sensor at the back, and that square sensor is on this focal plane. Watch, see how I pulled that back? That was great. Here's the horizontal focal point, what's called the principal axis. The principal axis. The optical axis is the vertical line. So principal axis is the horizontal line, and the optical axis is a vertical line, and where they meet is the optical center. And this is important because the optical center of a lens is where the least amount of bending, ideally no bending at all, happens. The light is essentially going to pass straight through the optical center and not bend. Right? And this diagram sort of shows it, doesn't show it very well. But every other line, every other point along this optical axis, the light bends more and more. And the further away you get from the optical center, the more bending happens. Focal length is the length from the optical center to the sensor, right? The focal length changes depending on the size of the lens. A shorter lens is going to have a shorter focal length. So in this case, this red triangle shows what a 17 millimeter long focal length would look like. The beauty of that is a shorter focal length means a wider view. And I'm going to skip right to these diagrams. So what happens is because the lens is physically longer, the optical center is physically further away from the sensor. And that means that the focal length is longer, right? And it's also true with a wide angle lens. A wide angle lens is physically shorter. The optical center, which is this circle, is closer to the sensor, which means the focal length is shorter. Well, the byproduct of those two things is by having a longer focal length, you get a narrower angle of view, but because you have more glass, you have more magnification, which means you can see things further away. Back here, you have less magnification because there's less glass physically in the lens, but you get a wider view, right? Let's have a look at this simulator. What is this simulator all about? This is where you are standing. If you're standing on this beach, this is how it looks, right? But it's not how it looks because this is only 14 millimeter focal length. Remember what I said, human eyes are about 50. So if we set this to 50 millimeters, a person standing on this beach would see this scene. If you were standing at that position from, now remember, we haven't moved anything. We just changed focal length here. If we go to a super wide angle lens, you see this really wide shot. A human being standing in this position would not see this because it's wider than our single vision focal length. There are exceptions to this, and just give you a minute. But if we go to 40 to 60 millimeters, let's say 50, oh, close enough, that's what it would look like to your eyes. That's a 50 millimeter lens, which is also called sometimes a portrait lens, right? Which is kind of your standard lens that comes with a DSLR when you buy it. It's closest as it can be to your own eyes, depth of field, focal length, etc. But as the lens gets longer and increases magnification, the lighthouse comes into view, and you'll notice that down here in the center, this diagram showing the angle of view is getting narrower. And what do I mean by that? Well, if I zoom all the way in and you're seeing just the lighthouse, how much are you seeing either side of the lighthouse? Not very much. If we go back to our original position, oh, almost there. Well, look at that. You see where the cursor is? That's it. All you were seeing was essentially the size of the finger on this little cursor. Nothing else. So it's a very narrow, it's a line, if you run that line up and down, that's a very narrow angle of view, right? So as focal length increases, angle of view decreases. So a wide angle lens, 28 millimeters is a wide angle lens, right? So there's a rough wide angle lens. A fisheye lens is probably closer to 14. Now this isn't showing fisheye distortion. We'll talk about that in a minute. But a fisheye lens is really a super wide lens because this is a simulation, you don't see it. And that's about 81 degrees. Now remember that the human angle of view, or 110, I'm sorry. The human angle of view is wider than 110. It's effectively 135, but because our head and eyes are moving, even unconsciously, we fill in those edges that even the camera can't see. But if we take that out of the equation and just look straight ahead and don't scan, the human eye is about here. Okay? Okay, so here's a question. Does the zoom function on a camera work by increasing the focal distance? Yes, effectively. It's exactly what happens. The zoom lens So what a zoom lens is, it's multiple lenses in the same barrel. It's a regular lens, or depending on how the zoom lens ranges, it could be a wide angle lens to a zoom lens in one container. So to get the functions of a zoom without the zoom, you'd have to change lenses and go to a longer focal distance, which means you could focus further away, right? That's what focal distance is. The item in focus is further away, and a zoom or telephoto lens, right? Tele being distant photo lens, could bring that focal distance, make it longer. A shorter lens, a wide angle lens, is going to have a shorter focal distance just by definition, right? However, there's other things that affect focal distance like aperture and exposure, which we're not going to talk about today, but that's certainly true that a zoom camera does change the focal distance. So our eye scan. So here's a couple of facts and stats about the human eyes and focal length. So human eye has a focal length of about 22 millimeters. So from the eyeball lens to the retina, it's about 22 millimeters depth. Not the same for everyone. So this is important to remember, that not every eye is the same. These numbers are not locked in stone for humans because we're all different. We all have different eyes. A camera with a 22 millimeter focal length is about 88 degrees, right? So it's pretty wide. And I already said our central angle of view, 40 to 60, so 50 millimeters is a good compromise. The effective, though, however, as I said, field of view of our eyes is 135 degrees. And that last point should say focal length, but it's the same as a lens with a 1 millimeter focal length. Okay? So 1 millimeter, by the way, that means that the focal length of the camera, of the lens, is 1 millimeter away from the sensor, physically. Because focal length is a physical distance. Okay, angle of view is sometimes called field of view. 50 millimeters is normal. And it's not what we see. Remember, cameras can't see what we see, but it's a close approximation with minimal distortion. All right. So how do we get a wider view than 50 millimeters if we have a 50 millimeter angle of view per eye? Because we have two eyes and the brain fuses them together. Okay, and we actually get a bit wider than the 50 plus 50, which would be 100 degrees. We get about 135 degrees. Part of it's because of our nose. So you'll notice that it's hard to tell from this diagram, but one of the lines of vision is blocked by our nose. Right? Our noses can get in the way depending on your nose. Some people have wider view because they don't have their nose in the way. The ridge of their nose isn't as prominent. Some people can only, I can see my nose if I look at it. I can detect it. But after a while, remember, that's something else you should keep in mind. For most of us who can see our noses, your nose disappears after a while. Like you no longer see it. It's there the whole time, right? But your brain just, don't need that. We'll just delete it from our memory. Okay, so stereoscopic vision has a bunch of other features besides wide field of view. We're strictly talking right now about how stereo vision gives us wide field of view, but it also gives us depth perception and a few other features as well, right? I mean, without stereo vision, it's almost impossible to catch a ball coming at you because you can't estimate its speed. There's a whole bunch of other things you get from stereo vision. Anyway, I'm not going to go into too much detail here, except to mention the two different kinds of lens shapes in cameras. Spheric lenses, the eye lens is a spheric lens, generally speaking, but it can accommodate and become slightly aspheric. That's its magic trick that camera lenses can't do. In cameras, you get one or the other. Spheric lenses or a combination of spheric and aspheric. And all that means is that a spheric lens is a perfectly smooth sphere, circular shape on the outside, whereas an aspheric lens is not. I've got an image. So an aspheric lens looks like this. If a spheric lens is equal curve on both sides, aspheric lens has kind of a bulge. It just means it's not perfectly spherical. It could be a bulge, it could be an indent, right? Anyway, let's go back. So who cares? Why do we care about this? Well, because aspheric elements can give you better lenses, quality lenses. So when you're buying lenses, see if it has aspheric elements, because it means it'll have fewer elements inside, they'll have a sharper image, but they're harder to make because they can't be ground, they have to be molded.